So welcome all to week 10 tutorial for the course Essential Mathematics for Machine Learning. I'm Pintu Kumar. I'm a PhD scholar at IUR IT Bombay. Today I'll cover topics related to week 10 content cover in the course. So the topics that I intend to cover today are some basics of set theory. This would be a very brief introduction because I think most of you would know. If there are some points that you don't know about this topic, then please feel free to ask those points and I'll try to clarify them. And then we'll talk something about some basics of probability, where I'll also talk about discrete random variables and continuous random variable and their properties. Okay, so first of all, for the sets, I'm moving very fast. So at any point, if you're not familiar with the terminology that I'm saying, please either type it in the chat box or unmute yourself and stop me there, because I think these are some basic stuff that you might have done in your class 11, 12. So I'm not going for that. Okay. So most of you know what a set is. So as NCERT says, sets is a well-defined collection of data. So if you are constructing a set out of something, you must be sure, or you must know a rule on basis of which you can assign an element to a set, or you can say that a element don't belong to that set. Okay. So examples of a set would include, for example, set of natural numbers, set of real numbers, these kind of things. Okay. So the terms that I think you must be familiar with are unions of two sets. So let's say you have a set A and a set B. So a union of two sets A union B means you will include elements of both sets A and B. Okay. So if element is either in set A or it is either in set B, then it would be an element of A union B. So A union B would look something like 1, 2, 3, 4 and 6. Okay. Now, let's say what is intersection of a set? Intersection is of A intersection B is, it is a list of elements which is in both A and B. So which is common for both A and B. Those elements belong to the intersection of these two sets. So intersection of these two sets is just a singleton 2. Okay. Now, what's a complement? So for complement, first of all, you should know what is an universal set. So an universal set is the set which contains all possible elements that exist. Okay. So for example, if I define my S as 1, 2, 3, 4, 5, 6 as my universal set, then I can define the complement of A. So the complement of A would belong, so the complement of A would include those elements which are not in A but are there in the universal set. Okay. So the complement of A would look something like 4, 5 and 6. Okay. So so I'll just give you some more terminologies. Something called as null set. So a set having no element is called null set. Okay. So anybody has any doubt in these terms that I just discussed? Okay. So there is something known as De Morgan's law, which is related to set. So this symbol C on the top is for the complement. So this De Morgan's law says that if you take A union B and you take its complement, this is same as A complement intersection B complement. Okay. And the another form of De Morgan's law is that if you take complement of A intersection B, it is same as A complement union B complement. Okay. Okay. So there are two rules that you have done in class 12, but there is a question related to this in assignment. So I'll try to discuss it slightly in length. So let's look at this property. Okay. So let's say you have two sets which are your A, this is your set A, and this is your set B. Okay. Now you want to count the number of elements in A union B. Okay. Then how can you do it, right? So let's say so you want to count the number of element in A union B. You do sum of number of elements in A. Okay. So you take number of elements in A. To it you add the number of elements in B. So if you look at this Venn diagram, you can see that this portion of A intersection B is getting repeated twice when you are adding the number of elements in A and number of elements in B. So the next step would be to subtract the number of element in A intersection B. Okay. So this is a pretty simple formula for number of element in A union B, that is number of element in A plus number of element in B minus number of element in A intersection B. Why a minus sign? Because this portion is getting repeated twice. Okay. So you can extend this to number of element in union of three sets. So this is number of element in A plus number of element in B plus number of element in C. Then you have intersection of two sets minus number of element in A intersection B minus number of element in B intersection C minus number of element in A intersection C. If you draw a Venn diagram and you see in the similar fashion we saw, you will see that we have left out this portion. So we again at the end add number of element in A intersection B intersection C. Okay. So this is the formula that you might not have seen in class 11th or 12th, at least in the CBSE syllabus. So this is the number of element in arbitrary union of not arbitrary but any finite union of sets. So rather than 2 and 3, now we are sort of generalizing thing. So what is this? This would be again the sum of all sets. So if you have, for example, this is something like A1 union A2 and AN, then you will take sum of all one size sets. So this will be number of A1, number of A2, and so on till number of AN. Okay. Then for all the sets that you take intersection of two sets, you will have negative sign. Okay. So it would be negative n of A1 intersection A2 minus n of A1 intersection A3. Okay. And so on. So one thing that you should remember whenever you are taking intersection of two sets is that your let's say this is n of AI intersection AJ, then your I must be smaller than J. That is, you don't want to repeat this thing that again you are taking AJ intersection AI. If you look at the like when you had two elements, then you didn't include again a number of element in B intersection A. You just wrote it once, right? So that's what we are trying to do over here also, that we will write this intersection only once. That's why we are like imposing an extra condition that my I should be strictly less than J. Okay. So you will subtract all the intersection of two sets, okay, with condition that I is less than J. Then you will add all the intersection of size 3. Okay. Let's say this is AI intersection AJ intersection AK. Okay. So over all I which is strictly less than J, which is less than K. Okay. So you satisfy this condition and then you take sum of all the three intersections. Then you again subtract the 4 intersections. So you will do an alternate till the time you reach the number of sets that you have. Okay. Any doubt in the content covered till now? Okay. So here is a small question based on what we did. Okay. So it says that uh, in a survey conducted on 1000 customers, okay, it was reported that 750 like product X. Okay, so let's try to draw an Venn diagram of it. Okay, so it says that the survey was conducted in 1000 customers. So your universal set contains 1000 customers. Okay, so the number of elements in your universal set, so the number of element in this rectangular box that I have drawn is 1000, and it says that it was reported that 750 like product X. Let's say this is the circle corresponding to your product X, then there are 750 people who like this product. Okay, and also there are 420 customers who like product Y. Okay, so this says what is the least number of customers that like both the product X and Y. Okay, now if you sum up these two values, then you will see that 750 plus your 420 is 1170, right? So it is exceeding the number of uh, people on which the survey was conducted. Okay, so why is it happening? Because we are summing this portion twice when we are summing this blue circle and the purple circle, right? So what we know, that number of element in A union B. Okay, so this number of element in A union B must be less than equal to 1000, because the survey was conducted on 1000 customers. So this should be less than equal to 1000. Now this is equal to number of element in A plus number of element in B minus number of element in A intersection B. Okay, so this should be less than equal to 1000. Now this is 1170 minus number of element in A intersection B should be less than equal to 1000. So this means that number of element in A intersection B should be less than equal to 1170 minus 1000, which is 170. Okay, so this option is correct for you. Okay, any doubt in this question? Okay, so this was a similar question to what is mentioned in your assignment. So anything that you want to ask related to the set theory portion that was covered this week, because now I would be moving to the probability portion that was covered. So if you have anything to ask, not just what I covered, but whatever was there in the lecture also related to the set theory portion, you can ask right now. Okay, then I'll move to probability. Okay. So what is probability? So for me, what probability is, when you are not sure about an event and you want to make a prediction that a particular event would happen, so the probability gives you a measure of how likely that event is going to happen. So how likely it is for the event to occur. Okay, for example, if you have a coin and you toss it in the air, and I have to say like whether it is head or tail. Okay, so I can say that with 50% confidence that this is head, right? So there is a 50% likelihood, or I would say 0.5 probability of coin being head. Okay, so so if you are performing some, let's say, experiment, for example, in the example I mentioned, performing experiment would be to toss a coin. Okay, so the experiment can have several outcomes. Okay, if you list all possible outcomes, then you come up with something that is called as sample space. So, for example, if you toss a coin, okay, then its sample space would be head and tail. So, what are the possible outcomes that you can get out of it? It is head and tail. Okay. Similarly, for let's say if you roll a die, okay, if you roll a dice, then the sample space would be something like 1, 2, 3, 4, 5, 6. So these are the possible outcomes that you can get on the die when you roll a dice. Okay. Now the next thing that comes after the sample space is what is called an event. Okay. So an event is nothing but a subset of sample space. Okay. Event is nothing but a subset of sample space. For example, event can look like, so if you roll a dice and somebody says that it is either 1 or 2, okay, so the event would be something like 1 or 2, okay. So this is a subset of your sample space. So event can be a combination of possible outcomes or a particular outcome, but this is a subset of your sample space, okay. So now, so the question is then how do you convert this to probability? So you want to look at the your chances of getting this thing or the chances of an event happening. So how do you transform this thing to a number? Okay. So any probability function p, right, can be defined based on three axioms. The first axiom says that the probability of an event, okay, can be between 0 to 1. So if you are able to define a function which satisfies these three property, for you that defines a probability, okay. So it says that the value of this probability function should always be between 0 and 1, okay. This is my first axiom. Second axiom says that probability of the complete, this S over here is the omega that we wrote, the probability of the complete sample space is 1, okay. What does this second axiom mean? This second axiom means that you can't have an event which is outside of this S, okay. So what is S? S is the collection of all possible outcomes, okay. So what is the probability that anything among the all possible outcome happened? So that is 1, right? So if you have, let's say, a coin toss, okay. So what is the probability that either head or either tail occurred? So the probability would be 1 because there is no other option for the coin to happen, okay. So this is what the second axiom says. Now the third axiom says that, okay, so here there is a term called mutually exclusive event. So mutually exclusive event are the events which can't occur together, okay. So I'll just define what is mutually exclusive event. So if, let's say, E1 and E2 are your events, then they are called mutually exclusive if E1 intersection E2 is empty, okay. So this is what is meant by mutually exclusive event, that these events can never occur together, okay. So if you have some finite number, even countable number of mutually exclusive event, then the probability of their union is nothing but sum of their probabilities. So this is the third property that this probability function should satisfy, okay. So if any function is satisfying these three axioms, then that is known as a probability function. Okay. So an example can be, so let's take a case of a roll of a die. So what is the sample space that you have? So sample space would look something like 1, 2, 3, 4, 5, 6, right? Now you want to define probability for every event, right? So let's define probability for singleton event, and then we can extend it to the probability of every event. Okay. So let's say the dice was fair and the chances of occurring every element on the dice is same. Then my probability of 1 would be same as probability of 2 would be same as probability of 3, and so on, which would be 1 by 6. Okay. So now based on this rule what I have defined, I can extend this to probability of any event that can occur. So let's say somebody asks me like what is the probability of 1, 2 or 3, like occurring either 1 or 2 or 3. Then I can see that this set that I have constructed 1, 2, 3 is nothing but 1, 2, union 3, right? And these all three sets are mutually exclusive because their intersection is empty. Then I can just take the sum of these probability. So this would be probability of 1 plus probability of 2 plus probability of 3. That is again this would be 3 by 6, that is half. Okay. So this is the basic idea of probability. Anybody has any doubt in this? Okay, so we move to something known as conditional probability. Okay, so I think I discussed probability a little bit, but most of you would be aware of it. So what is conditional probability? Let's say you have two events, E and F. Okay, and initially you have to find, let's say, probability of E when you are given no information about it. Okay, so let's take an example that you have a dice to roll. So the possible outcome is 1, 2, 3, 4, 5, 6. Now some E is the event that your the number on the dice is even number. Okay. So what is probability of E? So there are three choices where you can get even number on your dice, right? So the probability of E would be 3 by 6, that is half, right? Now let's say some of you like you are two friends playing and the second friend asked you to guess, and he asked you what is the probability of E. You would guess that it is half, right? Now he gave you an extra information. So F is the extra information that he is giving. The information that he gave you is that the number is less than 3, is let's say less than equal to 3. Now he is saying that after the extra information that he has given, okay, what is the probability of E? So that is what is known as the conditional probability. So it is represented by this line here. So this means that given F, that you have been told that F has already occurred. So you are sure that F has occurred. Then what is the probability of E? Okay. So in this case, if you see that you have been told that the uh, number is less than equal to 3, then you have only one even number over here and you have three choices. So what is the probability of E given F? This would be 1 by 3, right? So let's say E and F are any two arbitrary sets. So let's look at this thing. So when you talk in terms of Venn diagram, let's say this is your S. Yes, right. So If you look in terms of, let's say this is your sort of Venn diagram, then what is probability of E? Probability of E is nothing but number of elements in E. Let's say this is sort of discrete. If this would be a continuous sort of set, then this would be something known as measure. I am just quoting this, you need not know. Okay, let's replace measure by area. Okay, so this would be area of this circle E divided by the area of S. That would be the probability of your E. Over here it would be number of element in E divided by the number of element in S. Okay. So now after you have been given, so that you have an extra information that F has already occurred. Okay. Now your sample space or your universe reduces to just F, because you know that the F has already occurred. Okay. Now what is the probability of E given F? Probability of E given F would be that the number of elements of E inside F, that is your probability, this is number of element in E intersection F, divided by the total number of element in F, right? Because now your reduced universe is just this much. So you know that F has already occurred. Then you want to find what is the probability of E. So you just look at this much portion. This is the sort of intersection, right, of your E and F divided by number of F. This is your formula for probability of E given F. Now if you divide denominator and numerator by n of S, if you divide both of them and you divide the denominator also, then you get nothing but probability of E intersection F divided by probability of F. So this is the formal definition of your conditional probability. That probability of E given F is nothing but probability of E intersection F divided by probability of F. Okay. So let's try to apply this example on the example that we solved sort of by hard force, and see if this thing is applicable over here. So now if you look at this thing, what is probability of E given F? So here E was the event that the number that I obtain on my dice is an even number, and F was the event that number is less than equal to 3. Okay. So what is E intersection F? So there is only one element, right? So probability of this would be 1 by 6, right? Now what is my probability of F? Number is less than equal to 3 is 1, 2, 3, right? This is 3 by 6. I obtained 1 by 3, and this is same is what we obtained by counting explicitly. Okay. Any doubt related to the definition of conditional probability, or what does this mean, or how can we solve problems based on it? Okay. So here is a question based on conditional probability. So the question says that a bin contains 5 defective that would fail immediately if put in use, 10 partially defective, so that would fail after a couple of hours of use, and 25 acceptable transistors. Okay, a transistor is chosen at random and put into use. If it does not immediately fail, then what is the probability that it is acceptable? Okay, so let's use some notation here. So let's say D denote that the transistor is defective. Okay, so P denotes that it is partially defective, and A denotes that it is acceptable, right? So now what is asked? that if it does not immediately fail, so it is given that it has not immediately failed. So that means the transistor is not defective. So we are given D complement, okay. And what we have been asked to check, what is the probability that it is acceptable. So this is the quantity that we have to evaluate, okay. So, so what it would be, that is probability of A intersection D complement divided by probability of D complement, right? This is what we have to calculate. So what is A intersection D complement? So what is the total number, first of all, transistor? This is 10 plus 5, 15 plus 25. This is 40 transistors that we have. So A intersection D complement would mean just the A, because let's draw this sort of diagram. So there are 5 defective. All of them are now sort of mutually exclusive event. 10 of them are, this is defective, this is partially defective, this is 25, and this is acceptable. So what is A complement, A intersection D complement? That would be just this portion. So this is 25 by 40, okay. And what is probability of D complement? D complement has 35 elements. So 35 by 40, this is nothing but 5 by 7, okay. Okay, Ishita, can you please tell me which portion of this conditional probability was not clear to you? You can type it also if you want. If it was not completely clear, then also I can visit, but if it is some specific portion, please. Okay. So, okay, I'll try to do it once more. So, first of all, was the notation clear to you? What does this, let's say, probability of A given B means? Okay. So now the derivation part was not clear to you. That's fine. Okay. So let's say you have two events. This is A, this is B. This is A, this is B. Okay. So what is probability of A given B? We have to calculate, right? Now, what does A given B means? That you know that B has already occurred. Okay. So the information available with you is that B has already occurred. Okay. So if you look at the total number of possibilities, that is now the total number of possibilities that can occur. Okay, that is n of B. So n of B is your total number of outcomes. Okay. And if your B has already occurred, what is the possible number of outcomes for A? Now, because B has already occurred, this portion can't occur, the portion I shaded in green. Okay. So the portion that can occur is your this A intersection B, right? So what is possible number of outcome? Your possible number of outcome is number of element in A intersection B, right? Is this much clear? That your possible number of outcome, when you talk about P of A given B is a number of element in A intersection B, and total number of outcome is your number of element in B. Okay. So what is probability? Probability is possible number of outcome divided by total number of outcome. That is number of element in A intersection B divided by number of element in B. Okay. Now what we want to do is, this definition is also correct. Okay. But what we want to do is, we want to write this in terms of some probability. Okay. So that when we are calculating, our life becomes a bit easier. So what we do is, we divide the numerator and denominator by number of element in your sample space. Okay. So you divide your numerator and as well as your denominator by number of element in your sample space. So now this would be nothing but, the upper part would be probability of A intersection B, because this is your total number of outcome in N intersection B, and this is your total possible number of outcomes. Okay. And the denominator would be, sorry, this should be B, right? This is B in the denominator. This would be probability of B, right? So that's how we reach to the definition of probability of A given B. That is probability of A intersection B divided by probability of B. Am I clear? Ishita, was I clear? Okay, thank you. Okay, let's see if I have some more questions on this. Yeah. So I will zoom out the question and will give you 2-3 minutes to solve. Just try solving the question so that it is more clearer to you all. Okay, then I'll solve the question.
Sir, please explain the previous question. A bean content have defective.
So the last question.
Yes, sir.
Okay. Okay, I'll do this question again because okay. So I'll read out the question first. So a bin contains 5 defective, so that will fuse or fail immediately after it is put in use. 10 partially defective, that will fail after a couple of hours of use, and 25 acceptable transistors. If a transistor is chosen at random, what is and it is put into use, if it does not fail immediately, what is the probability that it is acceptable? So let's say you define 3 events. So first event is that your transistor is defective. Okay. Second is that your transistor is partially defective. And the last one is that it is an acceptable transistor. Okay. So what is asked in the question? So it is given that it does not fail immediately. Okay, so it is given that the transistor does not belong to the set of transistors that will fail immediately. So you are given that D complement has happened, that the transistor didn't fail immediately. Okay. So what is the probability that it is an acceptable transistor? This is what you have to find. Okay. So this is the question mark that you have to find. So what is the formula for this as derived above? So this is probability of A intersection D complement divided by probability of D complement. Okay. Now let's calculate probability of A intersection D complement. So what is the total number of transistors? Sorry. So the total number of transistors that you have is 5 plus 10, 15 plus 25, that is your 40. Okay. So among these, so this would be number of element in A intersection D complement. divided by total number of transistors, that is your 40, right? This would be probability of A intersection D complement. Just give me a second. Yeah. Now, what is the number of element in A intersection D complement? So if a transistor does not fail immediately, what are the chances? Either it will be partially defective or it will be acceptable transistor. So what is the number of element in this set? This is 25, right? That it is actually a good transistor, acceptable transistor, divided by 40. Okay. Now what is probability of D complement? So D complement means number of element in D complement divided by 40, right? So the number of element not in D is 40 minus 5, this is 35, 35 by 40. So what is this conditional probability? This is 25 by 40 divided by 35 by 40. This is nothing but 25 by 35. So this is 5 by 7. Now is it clear? Whoever asked that time, is it clear to you?
Yes, sir.
Okay, thank you. Okay, so now let's go to the next question, and I would expect you guys to solve this. And I'll give you 3 minutes to solve this. So I'll start attempting it at 6:50. Okay, Ram will confirm if somebody else answers or whenever I solve. Okay. I don't know the answer, so I can't tell you whether it is right or wrong right now. Others also please try and let me know what you guys are getting. Okay, so we have two different answers. We need to check which one is correct. I'll give you 1 or 2 minutes more. Okay, so you guys are getting 0.18, and I also think that might be the correct answer. So for others, let me solve this question. Okay, so here also we have two events. The question says Miss Perez figures that there is a 30% chance that her company will set up a branch in Phoenix. Okay, if it does set up, she is 60% certain that she will be made manager of this new operation. Okay, what is the probability that Perez will be a Phoenix branch office manager? Okay, so there are two events. First is that, let's call it P, that the company will set up a branch in Phoenix. And the second event is that Miss Perez will be made a office manager, will be made a manager. Okay. So let's look at the information that is given to us and what is the quantity that we need to calculate. Okay. So the first line says that there is a 30% chance that her company will set up a branch in Phoenix. So probability of event P, so let's call it small p so that you don't get confused with probability, is 0.3, right? And if it does, that means you are given that the company has already opened a branch in Phoenix. So the given condition here is if the branch is opened, so the event that has already occurred is P, then there is a 60% chance that she will be made the manager of new operation. So this is probability of M given that the branch is opened in Phoenix. So this is 0.6. Okay, and what is asked? So the quantity that is asked is what is the probability that Perez will be Phoenix branch office manager. So the quantity that is asked is what is the probability of this thing happening, that a branch is opened there and she is made the manager. Okay, so this is the question mark. So now if you look carefully at the formula of conditional probability, this is P of M intersection P, right, divided by probability of P. Now you must know this, right, that this intersection thing is commutative in nature. So P intersection M and M intersection P is one and the same thing. Okay, so if you take this thing in the denominator, the left hand side, what you obtain is that the probability of M intersection P is probability of M given P into probability of P, right? So you are given with both these quantities. So this is nothing but 0.6 and this is 0.3. So you obtain 0.18. Okay, so 0.1 is the correct answer for this. Any doubt in this question? Okay. So yeah, let's move to the next topic. That is known as that is something known as independent events. Okay. So you call two events A and B independent of each other if occurrence of one event do not impact the probability of another event. Okay. So what does this mathematically means? Sorry, that let's say even if somebody says that B has already occurred, then the probability of A does not change. Okay, even with the extra information that B has already occurred, so it is not impacting your probability of A, and vice versa, that if you are given something about A, then the probability of B does not change. For example, let's say there are two cities, Mumbai and Delhi. If somebody says that it is raining in Delhi and he wants to he wants you to infer what is the probability of it raining in Mumbai, then because these two events are sort of not related, yeah, I'll get to that, right? So because these two events are not related, so the probability of it raining in Mumbai won't be affected by the event that it is raining in Delhi. So these events sort of become independent to each other. Okay. So how do you sort of intuitively define independent events? That probability of A given B is your probability of A, and your probability of B given A is probability of A. Okay. Now let's look at the this definition that I have written over here. If you replace this by the formula of conditional probability, this is this equal to probability of A. Now if you want to use this particular formula for your independent events, one thing that you should keep in mind is you have probability of B in the denominator. Okay, that means if this is 0, you can't use this formula, because then your left hand side would be not defined, right? So what people have proposed is they use an alternate formula. So they take this thing on the right hand side. So this becomes probability of A intersection B is probability of A into probability of B, right? So this is the alternate formula that is more common and used. So you can define independence in this way also, that if you have two events, then probability of A intersection B is nothing but probability of A into probability of B. Okay. So this is just if you like expand this expression of P A into A given B, you will obtain this formula. Okay. Any doubt in this? What are independent events? I guess I answered your question. What is probability of A and B? So intersection means and. So probability of A and B is probability of A into probability of B. Okay. So here is a question for you guys. So just type it in the chat box. So we talked about mutually exclusive event, right? What are mutually exclusive event? That E1 intersection E2 is empty, right? So the question is, if A and B are mutually exclusive, are A and B independent? So you are given that A and B are mutually exclusive. I'm asking you if they are independent events also or not. So please, whatever you think, please type it in the chat. So you are given that A and B are sort of mutually exclusive, and you are being asked whether they are independent events also or not. Yes, somebody is asking something. Yeah. So the correct answer is that they are not independent. In fact, this is totally opposite of independence, right? So mutually exclusive means that A and B can't occur together. Okay. So if you want to calculate, let's say you are given B and you want to calculate A, then this is always 0, because if B has occurred, A can't occur. So that means the event of B happening is impacting A lot, right? So they are not independent, but sort of totally opposite of independent. Okay. And you can see it otherwise also, that probability of A intersection B would be 0, because A1 intersection A2 is 0, and you want this equal to probability of A into probability of B, and you are not sure what is probability of A and probability of B. So you can come up with an example where these two values are non-zero, and you have got the intersection probability to be 0. Okay. Okay, so here is another question. So let's say A and B are two independent events. Okay. Then the probability of occurrence of at least A and B is given by, so this should be at least one of A and B is given by, so you have to choose among these. So, this is question is probability of at least one of A and B. So this would be 1 minus probability of uh, none of A and B. So the complement of this event is that at least one of A and B is that none of A and B occur, right? So this probability is given by 1 minus probability of none of A and B. Okay. So A complement intersection B complement, right? None of A and B means that A is not happening and B is not happening. Okay. Now, because A and B are two independent events, you can easily show that A complement and B complements are also independent event. You can prove it, right? Just using the formula or the definition that I mentioned. So this would mean that this is 1 minus probability of A complement into probability of B complement. Okay, so this option is correct. So if your A and B are independent, then your A and B complement are also independent, and your yeah, and your A complement and B are also independent. A complement and B complement are also independent. Okay. Okay. So because this is sort of a 2-hour long lecture, so I'll take a break of 5 minutes. So we'll start again with this theorem of total probability and Bayes theorem in 5 minutes. So we'll start at 7:08. Okay. So just a break of 4-5 minutes so that you don't get bored. Okay, we'll begin. Okay. So this green line, the outer boundary, okay, that I'm overwriting it green. Let's say this is your sort of sample space. Okay, a weird looking one, but let's say this is your sample space. Okay. Now, let's say your B1, B2, B4 is a partition of the sample space. What is meant by partition is that this breaks your set in such a way, if you see that B1 union B2 and so on till B4, this makes your complete sample space, right? So if you take union of all these B1 and B2, B3, B4, it will be the complete of your sample space, right? And the intersection of anyone with anyone, so Bi with Bj, is empty, right? So they are not overlapping and they are sort of covering the entire space. So this kind of structure is called partition of any set. Okay. So for example, let's say this is your sample space. This is your B1, this is your B2, and let's say this is your B3. Then this is not a partition because you have some overlap over here. This is not a partition. Okay. So just a second. Yeah. So let's say you have a partition of this set, that is your B1, B2, B1, B3, B4, and you have some event A, and you want to find the probability of A. Okay. Then this is given by probability of A intersection with B1 plus probability of A intersection with B2 and so on. And this is also intuitively correct, right? So if you want to see the number of elements that you have in this A, that is nothing but the number of element you have in A intersection B2, right, plus the number of element in you have in A intersection B3, then number of element you have in A intersection B3, sorry, B4. And same thing translates to probability, that it is same as you take the probability of this much portion first, right, and you sum to it the probability of this much portion, and then you sum the probability of this much portion. So this is something that is known as a theorem of total probability. So let's say you have, I'll more formally write it. Let's say Bi, so this is a collection, okay, is a partition of your sample space. Okay, this is sigma. Then probability of A is given by summation over I probability of A intersection Bi. Okay. Now we want to extend this definition or the theorem in terms of conditional probability. Okay. So we know that probability of A given Bi is probability of A intersection Bi divided by probability of Bi. If we take this denominator this side, we can replace this thing by summation over I probability of A given Bi into probability of Bi. Okay. So this is just another formulation for this, right? So yeah, this is what is your theorem of total probability. We'll be using this in our Bayes theorem, right? Right now it might not look very important, but we'll be using it in Bayes theorem. Okay. This is Bayes theorem, okay, and probably the one of the most useful thing that you will encounter when you're whenever you're doing machine learning. Bayes theorems are used at a lot of places. Okay, there is a very vast area that is known as Bayesian learning, and those things which are many a times motivated by this Bayes theorem. Okay, so let's look at it. What is Bayes theorem? So this is probability of A given B. So if you look at it, overall, this is your base theorem, that let's say you have A given B and you know the probability of B given A. So you want to reach from A given B to B given A, then this is what you use. Okay. So this is probability of B given A into probability of A divided by probability of B. Okay. So let's sort of try to derive it. So you know probability of A given B, we want to reach to the point probability of B given A, right? So this is probability of A intersection B divided by probability of B, right? Now, if you want to convert this thing into probability of B given A, how can you do this? So if we divide this top portion or the numerator by probability of A, okay, then we are done, right? So what we do is, for the numerator, we divide and multiply by probability of A. We divide and multiply by probability of A. And we have a probability of B in the denominator, okay. So this portion becomes probability of B given A into probability of A divided by probability of B. Very easy derivation, but very useful derivation. Okay. So we will try to solve some question based on it. And I think there are a couple of questions in your assignments also. Okay. So the question is, just read the question with me. There are 3 coins in a box. One of them is two-headed. So the coin is not a fair coin now. On the both side we have head, the Cholet coin, right? Somebody is joining. Okay. And the another coin is a fair one. Okay, so the first coin was a two-headed coin. The second coin is a fair coin. And the third coin is a biased coin. Okay, so there are 75% chances of head coming up. So for the coin 1, we have two head. Coin 2 is a fair one. So 50-50% chance. And coin 3 has 75% chance of head and 25% chance of tail. Okay. Now the question is, if a coin is drawn at random, okay, if a coin is drawn at random from the box and shows head, so what is known to us is the outcome is head, because it is given that the coin is drawn from the box and it shows head. Okay, so what is given to us is that it is head. Then the probability that it is a two-headed coin. So what is the probability that the coin is the first coin? This is what the question is. Okay. Now, if you look at the information that was available to us, so if it is the first coin, given that it is the first coin, what is the probability of head? Probability of head is 1, because both the side is head, right? So given that the coin is second coin, what is the probability of head? This is 0.5, because this is a fair coin. And this is 0.75, right? Also, yeah, so this is what is given to us and this is what we calculate. We want to calculate. Now, if you remember the base theorem, when we want to switch from A given A to B given A, we use this base theorem, right? So here also the information given to us is in form H given something, and we want to calculate 1 given H, right? So we use base theorem on it. So probability of 1 given H is nothing but probability of H given 1 into probability of 1 divided by probability of this would be H, right? So now if you look at these terms, the first one is something that we know. This is the term that we the information that was already available with us. Okay. If you carefully look at the second term, so what it is saying is that you had 3 coins in the box and you picked up one coin randomly. Okay, so what is the probability of getting either coin 1 or coin 2 or coin 3? It is 1 by 3 for all three of them, right? So probability of 1 is probability of 2 is probability of 3, which is 1 by 3. Okay, so there is an equal probability of getting all these three coins. So the second term is also sorted. Okay, so this also you know that this is 1 by 3. The only thing that you need to calculate is probability of H. So how do you calculate what is the probability of getting a head when you randomly picked a coin from the combination of these three special kind of coins? Okay, so what is probability of H? Here we will use the theorem of total probability, that is probability of H intersection first coin, because if you look at now your sample space, this is partitioned into three parts by either first coin or second coin or third coin, right? So this is probability of H intersection second coin plus probability of H intersection third coin. This is nothing but using the base formulation. So H given first coin into probability of first coin plus probability of H given second coin into probability of second coin plus probability of H given third coin into probability of third coin. Okay, so the first thing that we know that this is 1, and what is probability of first coin? This is 1 by 3 plus second coin, this is 0.5 into 1 by 3, and the third quantity is 0.75, right, into 1 by 3. Okay, so let's put this in the formula. So again, this is H given 1 is 1 into 1 by 3, right, divided by this complete thing that we had. Okay, so this is 1 into 1 by 3 plus half into 1 by 3, this is 0.75 is 3 by 4, right? So this is 3 by 4 into 1 by 3. So we have lot of 1 by 3s here, so we can take it common and cancel it out. So we'll be left with 1 by 2 plus 3 by 4. This is nothing but so we take 4 plus 2 plus 3 by 4. This is 4 by 9, right? I think this should be the answer. Yeah, we have an option of 4 by 9, and that is the correct answer. Any doubt in this question? Anybody has any doubt in this question? Okay. So this is what was about Bayes theorem. We'll move to random variable. There we'll just talk about expectation and variance. So any doubt till this point, please, you can just clarify right now. Okay. I'll motivate this random variable via an example. Okay. Let's say you toss two coins. Okay. You toss two coins simultaneously. Okay. So what is the sample space that you'll get? You'll get something like head head, head tail, tail head, or head head, right? But now somebody might ask you, uh, what is the probability that I'll get one head? Okay, only one head. Okay, then what you can do is either you can count that there will be two such possibilities and you can find 2 by 4. Other thing is you can define a map. Okay, you can transform this sample space into some numerical values based on your need. Okay, so that numerical value is something that is known as your random variable. For example, when I said that I want to count the number of heads, so you can define a random variable as number of heads. Okay, so for this particular example, if you look, What would be the possibilities for number of heads? This would be 0, this would be 1, and this would be 2, right? And for every value of this random variable, you will have some associated probability. Okay. So what is the probability that there will be 0 head? So sorry, the sample space should have TT over here, right? Tail. So there is one possibility out of 4. So this is 1 by 4. For one head, there is two possibilities. So this is 1 by 2. And for two head, again, it is 1 by 4. Okay. So this is how you define random variables, that from the sample space, you sort of try to transform it into some numbers and you assign some probabilities associated with it. Okay. So here is an example, another example. So the example says, let x denote the random variable that is defined as the sum of two fair dice. Okay. So you roll two dice. So what is the sample space that you obtain? This is a sort of a big one. So this is 1 1, 1 2, right? 1 3, 1 4, 1 5, 1 6, right? Here also you get 1 2 1, 3 1, 6 1, right? At the end you get 6 6. Okay. So this is the sample space that you have. This is a sort of very big sample space, and if you are just interested in the sum of whatever you get on dice, why worry about this big sample space, right? So you can define the random variable as sum of two dice, right? So what is the values that this sum can have? So the minimum value that it can have is your 2 when you sum 1 and 1, and you can go all the way till 12, right? So you now also have some associated probabilities. Okay. So what is the probability of x being 2? So you have only one possible outcome. So this would be 1 by 36. What is the possibility for sum is equal to 3? So you have two possibilities now, right? So this was for 1, this is for 3. So this is 2 by 36. Now for sum is equal to 4, you have three possibilities, right? So for 4, you have three possibilities, and so on. You can just define till the end. In the middle, you somewhere at 5 6 7. So this is 4 by 36, this is 5 by 36, you will get 6 by 36, and from here on it will reduce. This will be 5 by 36 and so on. Okay. So I can assign an arbitrary value to outcome of an event, right? So generally those are numerical values, and whatever values you assign, you have some associated probability with it. Okay. Okay. So now if you have a random variable, right, then it can take two kind of values. Okay. So either the values that it take is discrete. So for in the last two examples that we did, so the values that we obtained were discrete. What is discrete? That there is some gap between the values that we are obtaining. So these kind of random variables are known as discrete random variables. Okay. So, and this probability function that we define on x, right? This thing is known as probability mass function for discrete random variables. Okay. Again, if your random variables that you are defining are sort of continuous in nature, okay, they take continuous value. For example, let's say this is your graph and this is your p of x, and these are the values of x that it takes. Okay. Okay. So if it takes continuous values, then those are called continuous random variable. And for them, the p of x that you define, that is not known as probability mass function, but those are known as probability density function. Okay. Or in short, you can call them PDF. Okay. And this is called PMF in short. Okay. The next thing that comes here is something known as CDF of a random variable. Okay. This is the cumulative distribution function. Okay. So what is CDF? So let's say this is represented by, generally represented by small f, both this probability mass function as well as your probability density function. And this your CDF is represented by capital letter F. Okay, many a times you will find it represented by capital letter F. So f of x is x, sorry, this is, yeah, this is your probability of your, so let's say this is some point A, so x less than equal to A. Okay, so I'll give you an example. Okay, so for this cumulative distribution function, so this means that probability that your random variable, that whatever you are getting, is less than equal to A. Okay, so let's take the dice example for simplicity. So there we had based on number of heads we obtain, we had a random variable taking value 0, 1 and 2. The probabilities were 1 by 4, 1 by 2 and 1 by 4. So what is the cumulative distribution function at point 1? This is the probability that your x is less than equal to 1. So less than equal to 1 means that it is either 0 or it is 1. Okay. So this is probability that x is equal to 0 plus probability that x is equal to 1. Okay. So this is nothing but your half plus 1 by 4, and this is 3 by 4 for you. Okay. So this is something that is known as cumulative distribution function. I have not touched upon this random variables in very detail. There are many important sort of examples also of some structures that are related to these. For example, you have many famous distributions such as Bernoulli distribution, okay, which are sort of useful even in your machine learning tasks. Okay, for continuous cases you have normal distribution. So at any point where you model your noise in your machine learning models, the most go-to distribution for that is your normal distribution. Okay, there are like a family of machine learning algorithms that are based on your continuous distributions. So I wouldn't have done justice in the time allotted to me. So what I can do is I can refer to you a book where you can read more about if you are sort of really interested. Okay, and for others, I'll try to solve questions, something which is similar to your assignment. So who have joined for assignments, you can see the question that I would solve. But if somebody is really interested in exploring more about the distribution, then you can refer to this particular book. This is a very sort of famous book by Sheldon M. Ross. There are many books by Sheldon M. Ross, but I find this book good for sort of beginner to intermediate level. So the book is titled Probability and Statistics for Engineer and Scientist. So chapter 2 onwards, you will find a lot of details about this thing. Okay. Mm, my pen is not working. Ah, it is working now. Okay. So you can refer to this book, whoever is interested. Okay, the author is Sheldon Ambrose. This is a very common book. So now we go to something known as expectation. This is also called as mean, okay, or average. Okay. So if you have some random variable, okay, so let's say like when you talk of average, you want to take let's say average of numbers 1, 2 and 3. What would you do? You would do 1 plus 2 plus 3 divided by 3, right? Whatever value of it. Now if somebody says that the chance of 1 occurring is just 0.1, chance of 2 occurring is very high, let's say this is 0.8, and chance of 3 occurring is also very low, that is 0.1. And now he's telling you to take sort of weighted average based on the chance of their occurring. So what would you do is you will multiply them with their chance and then take the average. Okay, here all of them had equal chance of occurrence, right? So that's why we were sort of what we were doing here is 1 into 1 by 3 plus 2 into 2 by 3, sorry 1 by 3 plus 3 into 1 by 3, and then we obtain this formula. If you do just this much, you will get something that is known as your expectation. Okay. So this is what is written here mathematically, that expectation of a random variable is nothing but xi into probability of xi. So this was the xi, and the second row was the probability of xi, that is the chance of its occurrence, and we sum it up. Okay. So this is what is meant by expectation. So here is a question. So let's say x is the outcome when we roll a fair die. What is expectation of x? So when we roll a fair die, you get 1, 2, 3, 4, 5, 6, all with probability 1 by 6. So what is the expectation of x? So this is summation of I is equal to 1 to n xi probability of xi. This is 1 into 1 by 6 plus 2 into 1 by 6 plus 3 into 1 by 6 and so on till 6 into 1 by 6. This is nothing but 1 plus 2 plus 3 plus 4 plus 5 plus 6 into 1 by 6, which is your 6 into 7 by 2 into 1 by 6. This is 7 by 2. It is 3.5. So expected value of your dice roll is 3.5, but you can never get 3.5. Okay. So yeah, this is sort of what you get. Okay. So here is another question. I'll give you 2-3 minutes. You guys attempt this question, then I'll solve this question. So again, you again roll a die. Okay. So, but this die is not same as your earlier die. It has 1 on 3 of the faces. So on a regular die, you have 1, 2, 3, 4, 5, 6 written on it. But in this form of die, you have 1 written on 3 faces. Okay. And 2 written on 2 faces and 5 written on the last one. Okay. And you have been asked to find the expected value for this random variable when you roll the die. Okay. So I'll give you time till 7:39. Please solve this question. Okay, I'll wait for 1 minute more, then I'll try to solve and see what answer I get. Ishita, I think the answer would be from the options only. So 2.167, I don't think that would be an answer, but I'll check. The answers can also be wrong. But you can just cross check your calculations. Okay, let's try solving this question. Okay, so now if you have only 1, 2 and 5 on the faces, so your random variable can take only 3 values, that is 1, 2 and 5, right? And you have 1 on 3 faces, so probability of getting a 1 is 3 by 6 because you have it on 3 faces, right? Probability of getting 2 is 2 by 6 and probability of getting 5 is 1 by 6, right? So now if you take the expected value of x, this is 1 into 3 by x, 3 by 6. So this is x into probability of x plus 2 into 2 by 6 plus 5 into 1 by 6. Okay. So this is 3 plus 4 plus 5 divided by 6. Did I make some mistake? I think I have not. So this is 7 plus 5, 12 by 6. This is 2. Okay. So this is how you get 2 in this. Okay. Okay. So here is a question. You are given with a discrete random variable w with probability mass function. So probability mass function is nothing but the probability assignment that we did just here. So this assignment is known as probability mass function, as I mentioned earlier also. So this is given by w by 15. Okay, for w 1, 2, 3, 4, 5. Okay, so your w takes values 1, 2, 3, 4, 5 with probability 1 by 15, 2 by 15, 3 by 15, 4 by 15 and 5 by 15. Okay. Then they are asking capital F of W 3.25. So capital F of W is the CDF, that is cumulative distribution function. So we have to find probability that my W is less than equal to 3.25. So less than 3.25 would mean that it is either 3, 1 or 2, right? It's either of these. So this is probability of W is equal to 1 plus probability of W is equal to 2 plus probability of W is equal to 3, which is nothing but 1 by 15 plus 2 by 15 plus 3 by 15. This is 6 by 15 or 2 by 5, right? So this is the correct option. Okay, any doubt till this point? Okay. Okay, so this is related to, I think, conditional probability. I sort of have included it late. So let A and B be two events such that probability of A is given to be 0.6, probability of B is given to be 0.2, and probability of A given B is 0.5. Then what is probability of B given A? This is a very easy question. I want you all to solve. So this will use Bayes theorem. I'll give you 2 minutes to solve this. After 1 minute, I'll write the formula for Bayes theorem. You can use it. And before that, you can just do it on your own. Okay. Just solve it and tell me what answer you guys are getting. Satish will confirm if somebody else also solves. Okay. So I'll just write the formula that you need to use. Probability of B given A is probability of A given B into probability of B divided by probability of A. So you have everything available with you. You just need to plug in the values. So yeah, this is 0.5 into 0.2 divided by 0.6, right? So this is 0.0, no, this is 0.1, sorry. So this is 0.1 divided by 0.6, which is 1 by 6, right? So this was an easy question, right? Okay. So before defining variance, I'll sort of try to motivate variance. So actually, this expectation and variance are not just exclusive to your random variables, but when you sort of collect some data, let's say uh, you trained your model, okay, and you are getting some level of accuracy, okay, but many a times you have some randomness in your training model, okay. So that randomness can occur due to your train and test split, okay, or or you are using some stochastic optimizer, okay, or some sort of stochastic optimization where your data points are not in same sequence. So it is not necessary that you get same value for accuracy every time you run your model based on the some stochastic parameters, okay. So generally it is good to report your average accuracy. You sort of train your model and test it, let's say 10 times, and then you report your average accuracy, okay. So let's say I'll motivate it this way, but variance are useful in lot other at lot other places also, but I'll sort of motivate in this place, okay. So you are getting an accuracy of, let's say 90%, again 90%, again you got 89%, and you got 91%, okay. So if you look at this model, then the average gets you to the 90%, okay. Another time when you trained, you got an accuracy of 80%, again you got 80%, you got, let's say 99%, and again you got 99%, okay. So now if you look at sort of this accuracy, so this would be also something around 89.5%. Now if you look at the average, okay, average is very similar to each other, right? But this model seems to be more trustworthy. Trustworthy in sense that I can depend on this model to get 90% accuracy uh, in almost every situation, right? But the second model that you have trained is falling to the accuracy of 80%. So this is not that. So stochastic parameter is a parameter that is not fixed but varies, okay. So stochastic means something that is not fixed but varies. For example, if you train your model. So what is the first step that you do? You split your train and test data set, right? So you say that 80% will be training data points and 20% will be your testing data points. Okay. So the 80% data point that you choose in training data set is not always the same 80% that you will be doing again and again. You can do that, but what generally people do is they will take some random 80% out of your complete data set and some random 20% they will keep it as test data set. And again, if you are repeating the experiment for the second time, you take 80%. It is not necessary that you will get the same data point that you got initially. So if there is slight change in data point, then that will reflect in your accuracy level also. There can be a slight change in data point. Okay. So like in many other part also, whenever you are training a model, the situation can arise that when you are retraining that model, some values can change, right? Some parameter values can change. So that is what is known as stochastic parameters. Was I clear? Okay. Ishita, was I clear? I hope so. Okay. So yeah. Okay. So the first model, uh, Ishita, train and test are not models, but part of your data set. So I'm not sure how well versed you are with any machine learning model, but when you start your machine learning model, what you do is you split your whatever data set is available with you, okay, into two parts. One of them you use for training, and based on whatever parameters you obtain after training, you use the second part for your testing purpose. Okay. Okay. Like if you are not very much aware about this machine learning model, then I would suggest you to either look at some introductory machine learning, some starting 1-2 videos of any course, or you can look at the previous recording for this course also. Earlier I have explained these things. Okay. Yeah, yeah, the other term is that the first one is precise, but mathematically we can say that the variance is less in this case. I'll define the variance. So what is variance? Variance gives you a measure of how far your data points are from the average value. Okay. So in this case, if you look that your average value is 89.5, so the data points are very far from your average values. But in this case, they are very close to your average value. So for this case, you will have a low variance. So variance is the like the change in sort of values. In this case, you will have high variance. Okay. Now, okay. So let's spend 1 or 2 more minutes. So let's say what I said is that the variance is the change from the mean value. Okay. So if you calculate the change from mean value in this case, this would be 0 plus 0 plus this would be minus 1 and this would be also minus 1. Okay. And there are 4 points, so let's divide it by 4. So this would be something minus 2 by 4. Okay. So this is not the variance, but I'm just saying like evaluating what I said. Okay. In this case, this is minus 9.5 plus 9.5. Okay. Sorry, minus 9.5. Again, this is plus 9.5 plus 9.5. So this thing is summing up to 0. 0 divided by 4 would be 0. But I said that this case should have high variance. Okay. Now what is happening over here is that I have large variation from my average value, but both the variations are in opposite directions, so their signs are getting cancelled. But we don't want this. So if there is a variation, we want to capture this change. Okay, so what we do is, rather than just looking at x minus your average, what we look at is, we take the square of this term. So rather than looking at just this thing, we look at the square, and then this value would become 1 plus 1 is 2, 2 by 4, and this would become 9 by 5 square plus 9 by 5 square plus 9 by 5 square plus 9 by 5 square, and we reach something as 9 by 5 square. Now this value is very high, right? So this is the motivation behind this square. Okay, so variance of x is nothing but your if you have some data points, this is summation from 1 to n, this is your x minus mu square divided by n. Okay, now when we talk in terms of your random variable, here the assumption for this formula was that every data point is equally likely. Okay, so now again, like in the average case, what we did was we multiplied them with their probability. So here also, rather than dividing by a constant average, this probability of 1 by n, so for a random variable we can define it in this form: x minus mu square into probability of x. Okay, so xi over here, right? This is what we can do, right? So this is nothing but same as, this is what is defined as expectation of x minus mu whole square. Okay, so variance of x is defined as expectation of x minus mu whole square, which is nothing but summation of 1 to n x minus mu square into probability of x. Okay, so this is one thing, but you can just derive this thing, that your expectation of x minus mu whole square is expectation of x square plus mu square minus 2 mu x. So this is a property of your expectation that you can split whatever is inside. This is not a property of variance. This is applicable only for expectation. So whenever you are solving, if you have something inside variance, please do not split it. Okay, for expectation you can split it this way. So you got expectation of x square minus expectation of 2 mu x plus expectation of mu square. Okay, and this is this 2 mu is a constant value, that's why it comes out of the expectation, and you get 2 mu expectation of x plus mu square. So this value is again mu, so this becomes minus 2 mu square plus mu square is minus mu square, and you get an alternate formula for your variance of x, which is given as expectation of just x square minus mu square. How do you calculate this first part, expectation of x square? This is nothing but summation of 1 upon n xi square into probability of xi. So in the mean, you used to do summation of xi p of xi. To calculate expectation of x square, you will do summation of xi square probability of xi. Okay, so let's calculate this variance of x when you are rolling a die. So earlier we have already calculated the mean. The mean of this thing was 3.5. Now we have been asked to calculate the variance. So the x takes 6 values, 1, 2, 3, 4, 5, 6. This is 1 by 6, 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 this is 1 by 6. 6, right? So to calculate variance of x, we want expectation of x square minus mu square, right? This is also denoted by mu. So we already have mu. We want to calculate expectation of x square. Okay, so this is nothing but 1 square into 1 by 6 plus 2 square into 1 by 6 plus 3 square into 1 by 6 plus 4 square into 1 by 6 plus 5 square into 1 by 6 plus 6 square into 1 by 6. Okay, so you can just evaluate this thing. This, I guess, would be, I have forgot that formula. So this should be 1 plus 4 plus 9 plus 16 plus 25 plus 36 by 6. Okay. So this is 5, 9, 14, right? 14, 20, 30, 55, 61, yeah, 91 by 6. There can be a calculation mistake here. So what is your variance of x? Variance of x is nothing but 91 by 6 minus 3.5 whole square. So you can evaluate this. So yeah, any doubts in this? So this was the content that I prepared for today. If you have anything to ask related to whatever we have, I'll wait for 2 minutes. If nobody has anything to ask, then I'll end this session.
Good evening, sir. I'm Satish here.
Okay.
In the current assignment, the question number 4, I felt somewhere it is the answers are not there. What we'll do if we feel that like